Hello class, my name is Bang Chen and my presentation is about the lossless compression by using the decreased cosine transform to dimension. The content of the presentation in the next slide. So the content of this presentation will be the first of all I will talking about the lossless compression technique. I also introduce the decreased cosine transform with the two dimensions, and the next two I will show how to apply the decreased cosine transform to compress compression on image by using the MATLAB code. At the end, I will show the limitation and the improvement. And at very the end, I will show the demo of my program. So at this slide, I will talking about the image lossless compression techniques. So the lossless compression will help reduce the image size, but like without any effect onto the quality. So the advantage of this method is will be um, of the lossless compression will be the win-win technique. It will be allow us to reduce the image size, but it will retain the important property of the image. So because it's advantage that this one we can use it in the medical field, military field, or another important purpose. It which require keep the quality of the image as possible as we can, but we can also allow it reduce the size. On the next, in this slide, I will introduce the decreased cosine transform two dimension. First of all, I will talking about the image. So as we know, with the image was built by a matrix of the pixel. It means this image we have like the horizontal column of pixel and vertical row of the pixel. So in this example, if we take the green line across the picture, we can see right here it will be a row matrix of the pixel. It include the multiple pixel in here, and those pixels have different color. We can see the bright, the dark, the gray. So the value of pixel will be the number from 0 to 255. The 255 standard for the brightness one, and the 0 standard for the darkness one. So if each pixel have the gray color, it will be have a value from 0 to 255. So if we plot the horizontal line of pixel into a chart, we can get a random decrease signal like the yellow line in here. With the uh, with the whiteness one is with the high value, and with the lower value for the darkness one. So right now we can convert from the pixel to the waveform signal. So how the relationship between the frequency and the value of the pixel. We will consider C2 onto the figure 2. If we check the color of like two pixels next together, if we see the color is change rapidly from dark to bright, bright to dark like this one, it means we have the value is change a lot from 0 to 55. from very low to very high. It means this way will be have the high frequency. In another way, if we have two pixels next together and change the color just a little, not have much difference in the color, so it means the value change from the pixel 1 to pixel 2 to pixel 3 is just a little. We have the low frequency right here. So up to this point, we can convert an digital image to pixel and to the discrete random signal. So we will perform this signal by multiple cosine waves. So in this example, I use like the A standard cosine wave from C0, C1 to C7 to perform the discrete random signal. I multiply the value of each pixel to the waveform and add them together. We will have the cosine transform. So this one is very familiar with the Fourier transform in the communication. So we have the coefficient formula x of k will be the x of n. This is the value of each pixel multiplied for the cosine function. This is called the cosine transform. For like 2 dimension, we treat the transform in different way. Where we can consider if we have we take a block of a pixel multiplied by a pixel. So total right here I have like 64 pixel. So with 64 pixel I have their value and I do the discrete cosine transform for the row by row. In the first result, this is the first coefficient. It will be a matrix of 64 and we take this first coefficient, we do another one of the discrete cosine transform, but in this time we do the by the column. It means like column by column. We will get the final result will be like the 64 matrix of the coefficient. So from the original of the image with the 64 pixel, we can use the discrete cosine transform 2 dimension to convert it to A by A equals 64 of the coefficient. So in the next slide, I will show how to apply the discrete cosine transform to the compress the image. To apply the discrete cosine transform 2 dimension to compress an image, first of all we have an observation like this one. Usually in those small log A by A pixel, the change in the color between the pixel to pixel is not too much. So it means the low frequency have more contribute in the block than the high frequency. So we can clearly see that by use the A by A block convert to the discrete cosine transform to 2 dimension. The purple matrix A the coefficient. So we can see those values on the top left will be have the bigger value than the value onto the bottom right. So in here, the value in the top right is used for the low frequency, while those value on the bottom right will be used for the high frequency. We can see that when we graph, when we plot the coefficient matrix into the power. So the yellow one indicate that it more high power than the purple one. Based on that observation, I write down a program to do the compress image based on the decreased cosine transform. So at the start of the right hand side is the flow chart of the program. At the starting, we will do the select an image and load it into the program. At very beginning step, we will do the decompose image, because as we know that with the color image, it will be contributed by 3 different channels: red, green, and blue. We will working on to channel by channel. We take each channel and we do the we choose A by A block in on the channel and do the decreased cosine transform 2 dimension for each block. After this step, we will have like A by A matrix of coefficient. It means we have total 64 of coefficient. Based on our observation, we will keep those coefficients for the flow frequency and suppress the coefficient for the high frequency. After that, we do to the invert the decreased cosine transform for the block A by A, and we keep doing it for the whole of the channel. And after the channel, we will do for like each channel. So if every pixel will suppress high frequency already, we will do the reconstruct an image, display the compressed image, and also show the size of the after we compress. And after that, we will calculate the compress ratio by take the value of the compressed image size divide for the original image size. Okay, I will show how the program works in the next slide. So in here, this is my application. I'm coding by the Matplotlib, and it shows step by step to do the compress image. First of all, we will do the choose the select image to load image to the program, and after that it will be show the image, show the name, and it also show the size of image. The second step, we will choose how many coefficient we will keep it. For example, in this case, I choose like 16 coefficient with the lowest frequency to keep and suppress another 48 highest frequency coefficient. So after I press after that in the step 3, I read the compressed image. I will got the result with the compressed image and with the size of it. We can see in here from the original is like 683, and in the compressed image will be 431, something like this one. The compressed ratio will be like 63, and the compressed ratio will be calculated by the compressed size image size divide for the original image size, like this one. So by to keep 16 of the lowest frequency, I have the compressed image very similarly with original one. We can see why this one we had that background, because it suppressed the high frequency already, so the background from white is changed to black right here. And with the 16 coefficient, we can see those property of the image is not changed too much between the uh, original one and the compressed image. So in this slide, I will talking about the limitation of this method, and also how to improve the lossless compression by the decreased cosine transform. we can see in the picture, if I choose the coefficient A to the number of coefficient is just one, I mean it just keep one or two coefficient and subtract the rest of them, the output image will be lose some quality. It will be a little bit different. So it means if we suppress too much the coefficient, we will lose the quality of the image. However, that's like the limitation of this methods. However, if we choose the number of coefficient is too big, the maximum is 64, we will get an original picture and it does not compress anymore. So that's why we must be choose the right value of the number of coefficient you give it. And if you want to extremely reduce the size of image, you must be beside you apply the de-rich cross-section film, you must be have the additional method, extra methods to reduce the size of the image more. So if I'm still working on this project, I have time, the improvement will be at the cost, maybe like the Huffman cost, to reduce more for the size of the compression image. Okay, so up to now, thank you class for listening my presentation, and this is my work site, and I will do the demo after this slide. Thank you very much. Hello class, this is my lossless compress program which I write out by MATLAB course. So I will demo to you guys how the program will work. First of all, I will select an image and I will use the image test number 2, open it. After I open the image will be loaded to the program with the name and with the size of it. I will choose the number of coefficient with the lowest frequency to give. For example, in this case, I choose 10 lowest frequency coefficient to give, and I press the compress. I will got the compressed image on the right hand side with the size reduced compared to the original, and it will also show we keep 10 and we subtract like 54 the high grade frequency coefficient, and the compress ratio is 0.56%. So we also to do another test by adjust the decrease cosine transform coefficient. We adjust to 16, or we can adjust to 22, 21. It means I increase the number of coefficient I give it. So, and I do the compress. So on the right hand side, we still have the image. It looks like very similar with the original, but we can see the size is increased and the compress ratio also increased too. But like when we reduce the coefficient to 1 or 2, we do the compress again, we will get the size smaller and the compress ratio also the smaller too, but we can see the quality of the image will be much different with the original. So that's why we must be choose the right number of the coefficient to keep. For example, in this case, if like 16, I think is the best one, because with 16 the compressed image and the original image, it look like similarly together, and the compressed ratio also like 0.6 enough to store or transmit. Okay, thank you for listening my demo, and bye bye.